What's up, everybody? Mr. Murray here, Mr. Murray's Mathland, and we're continuing in our series of free response review videos here, specifically for the AP Calculus exam. And I know that on the AB AP exam, this is almost always one of the 6 FRQs on the test, and that is interpreting the graph of a derivative. And it can usually be presented a couple different ways. One, where they flat out say, this is the graph of f prime, this is the graph of g prime, whatever. Or this way, which we're going to tackle today. And that is, we're shown that this is the graph of g, and then we're told that some other function, in this case h of x, is the definite integral from 1 to x of that function g. So the connection here is remembering your second fundamental theorem of calculus, or some textbooks call it the first fundamental, is that h is the definite integral of g. So that means when you take the derivative of h, you are talking about derivative of an integral that is going to cancel, and that's going to leave you with just g of x, and no chain rule there necessary. We're just replacing t with x. So when they say throughout this problem that this is g, that is h prime that you're looking at. And therefore, to continue with that idea, that h double prime of x is equal to g prime of x. As you can see in part A here, we're asked to find h of -1, h prime of -1, and h double prime of -1. So it's just good to realize what you have when you're approaching each of these problems. So first up, let's find h of -1. So h of -1 is just following that definite integral from 1 to -1. We're replacing x with -1 of the function g of t. And evaluating a definite integral given a graph, that would be using the area, between the graph and the x-axis. One thing you might want to watch out for here, though, is that these limits of integration are out of order. It goes from 1 to -1. So I always like to have my limits be in order, so I flip and put a negative out in front. That's what happens, right? Get the opposite value. And now I can interpret as I normally like to, which is area that's above is positive, area that's below, I'll assign a negative value to it. So in this case, we're going to get negative whatever this definite integral is, and we're going from -1 to 1 on the graph, -1 to 1. So that is this area of the semicircle here with a radius of 1. The area of a circle is pi r squared, so this is half of that pi r squared, and the radius is, of course, 1. So the area of that would be 1 squared is 1. So this semicircle in total is going to have an area of pi over 2. It would be below the x-axis, so you would assign it a value of -pi over 2 to represent a loss. But because you're taking the negative, because that was out of order, that means your answer is actually going to be positive pi over 2. So that's h of -1. Now, h prime of -1, which is the next thing they ask us for. So just using your relationship we just talked about, h prime is g. So h prime of -1 is asking for g of -1. And that's literally just looking at the graph of g and what's its y value at -1. So at -1, you're right here. The y value is 0. And there we go. H prime of -1 is 0. Easy, right? And lastly, h double prime. H double prime of -1, which would be g prime of -1. And that would give you, when you're looking at g prime represents the slope of the graph, that instantaneous slope at -1. And at -1 right here, as you notice, there's a corner or a sharp turn on the graph, or some people call it a cusp. So the derivative does not exist at a corner or a sharp turn. So, you could say undefined or no solution or something to that effect. And I guess I wouldn't say equals, I would say is undefined. And I would usually justify that, due to a sharp turn or a cusp. a corner, I think all those terms would be pretty acceptable to the AP graders, as long as you're telling them you know what you're looking at. And there we go. So that's part A. And it should be said that an FRQ usually has 3 or 4 parts to it. This video is going to be a little bit longer because I'm going to have 5 parts to this, because there's a few things they tend to like to ask, and I put all of them in this video. So I think this kind of covers a lot of the classic ideas that are associated with this type of problem. So here we go. Part B. Find all critical numbers for h of x. So a quick review of that. A critical number for a function is anywhere where h prime, the derivative of whatever function you're talking about, in this case h, where h prime is 0 or undefined. And remember that we've established in part A that h prime is g, right? And you don't need to reestablish that if you've shown that in your work in part A. You don't need to retell the grader every time. So where is g equal to 0? And again, that's just talking about its y values. And where is it equal to 0? 1 right here at -1, 1 right here at 1, 1 right here at 4. So x equals -1, 1, and 4. And there is no place where h prime is undefined. That would be, if there was a hole in this graph or some kind of asymptote or anything, but there are no breaks in this graph. So h prime, aka g, is defined everywhere within this interval of -3 to 5. And now for each one, determine if it's a relative maximum, relative minimum, or neither. And this is, kind of like your, first derivative test here, classic stuff. So you're basically looking to see, does h prime or g change signs, right? That's what you would do with number lines and testing left and right. So just no particular order here. At x equals -1, you see your graph right there does not cross the x-axis. It's below, it's still below. So h is going to have neither a relative min or max. And we try to support. It doesn't have to be a book, but since h prime or g does not change signs. Always good to, add a little extra justification. And usually they'll say justify to make it clear, but at x equals 1, our next critical number, look what's happening there. You're going from negative to positive. That's what the derivative is doing, right? So when the derivative changes from negative to positive, that means the original function is changing from decreasing to increasing, which makes it a relative minimum. So h has a relative or local minimum. And again, y, basically what we just said here, since h prime or g, I always like to write both. If you've already established that they're equivalent, you don't need to write both, but I don't know. I just like to. Since h prime or g changes from negative to positive. And I think that's perfectly sufficient. In fact, I know it is, but if you wanted to add, and thus that shows that h changes from decreasing to increasing, that certainly can't hurt if you got the time. But if you're pressed for time, this is kind of what we're talking about here, is how to justify these things and sort of what needs to be said here, a little test prep. And lastly, at x equals 4, you can see what we've got going on is kind of the opposite of just the previous one. The derivative is changing from above to below, so that would be h prime changing from positive to negative. So h will have a relative maximum or local maximum. You should be comfortable with both terms. And again, since h prime or g changes from positive to negative. And there we go. Okay, so those are so far a couple of really classic kinds of problems. And here is another favorite of the APs. I'm not sure why it's so popular, but it really is. Give the x values for the points of inflection for h. So I think maybe because the idea is that you tend to associate points of inflection with where the second derivative changes signs, and you're looking at the first derivative. So what you're really looking for is anywhere where the derivative h prime changes from increasing to decreasing, or vice versa. So you're essentially looking for relative maxes and mins on the derivative graph. So you can see increasing and decreasing right there. That's one. You're decreasing, then increasing. There's another one at x equals 0. Increasing, still increasing. Change to decreasing. Right there is one. And that's it. So I think you can kind of say this in one statement, or you can make 3 separate ones, but you're looking for where h, will have a point of inflection, or an inflection point, where h prime, again, or g, if you want to cement that connection, changes from increasing to decreasing, or vice versa. And that is an acceptable term. I always see written in their write-ups here, from increasing to decreasing, or vice versa. And this occurs at x equals, we said, -1, right there, x equals 0, and x equals 3. And there we go. And a lot of times people, kids will say, should our justification say this is where the second derivative changes signs? And, a big idea is that you should always try to justify in terms of what you're given. We're given g, which is h prime, so you should try to describe in terms of g or h prime what you're looking for. Not just a general rule that, hey, points of inflection are when the second derivative changes sign. I mean, it might not show the grader or convince the grader that you really know what you're looking for here. Anyway, so part D here, another kind of classic, is a little combination of the last couple ideas, and that is where is h, given interval where h is both decreasing and concave up. So, h will be decreasing and concave up. Again, when h prime, or g, is, and h will be decreasing when its derivative is negative. And h will be concave up when its second derivative is positive, but that means the first derivative is increasing. So that's what you're looking for here, is where is this graph negative and increasing. And that means when we say negative, we mean below the x-axis, having those negative y values. So where is this function below the x-axis and going up, essentially? So that would be right here, we're below the x-axis, going up. Also right here, below the x-axis and going up. And that's it, because the other spots were below, we're going down, we're decreasing. So and I think we've perfectly justified that. So this occurs over the interval -3 to -1. And this interval right here, 0 to 1. And you could use inclusive brackets on those kinds of things where you describe intervals of increasing or concavity, but you can also use open parentheses. Both are accepted. They make a special point of that in a lot of their conferences and write-ups. Okay, and so last kind of classic question. This is often one of the 3 or 4 parts of this question. So, I wouldn't feel I'd be doing it justice if I didn't include this. And that would be asking, where does h have a minimum or maximum value on a closed interval? Notice how they are, including the endpoints of -3 and 5. So when you're talking about a maximum or a minimum value on a closed interval, that's what we call the candidates test. And that means that the absolute max or min will either happen at the endpoints or at any critical numbers in the interval. So you don't have to organize your work in a table. It's not that I'm just trying to address these things that I have to check the endpoints, the values of h at the endpoints. So that would be -3 and 5, and any critical numbers in the interior of that interval. And we've already established that the critical numbers are where the derivative was 0 back in part B, I think it was. So -1, 1, and 4. And so now you've got to find h's values over those, at those specific spots. And so here we go. This is, sometimes a time-consuming part of the problem. So you want to at least be, ready for it and know what to do to save your time for actually doing it. So h of -3, finding h's value at -3 is following that definite integral, rule that you're going from 1 to -3. You're plugging it into that upper limit of g. And again, that's, out of order. So flip it, make it negative from -3 to 1. And we already found some area back in, part A, and I don't have it on the screen anymore, but this area of this semicircle was pi over 2. And between -3 and 1, you also have this triangle here, which is a 2 by 2 triangle. So its area is 1/2 of 2 times 2, or 2. And so then, being careful, of course, this negative that you have factored out, and then you're assigning a negative value to these because they're below the x-axis. So that's, an area of 2, but we call it -2, and area of pi over 2, so it's negative pi over 2. But when you take the opposite value of that, you get 2 plus pi over 2. So that's the value. I guess I'll try to keep my table neat here. 2 plus pi over 2. Okay, now h of -1, we've already found that back in part B, so we don't really need to find it again or show it again. That had a value of pi over 2. At 1, this kind of works out nicely. H of 1 is the definite integral from 1 to 1. And remember, whenever the upper and lower limit are the same, there's 0 area captured because you haven't, changed it all. So that has a value of 0, so that's pretty easy. Now you do have to find h of 4 and h of 5. So h of 4, I'll use a little green for that, again, is going the definite integral from 1 to 4, so that goes in order. I don't have to do any flipping. The area under g, between g and the x-axis. And that between 1 and 4 is a nice triangle. It's a base of 3 from 1 to 4 and a height of 1. So 3 times 1 is 3, and then half of that is 3/2, or 1.5. And again, it's positive because it's above the x-axis, so that's like a gain. And lastly, h of 5. Now h of 5, we just really have to go one little further bit here. And you're going the definite integral from 1 to 5 on g. And you just did 1 to 4 is 1.5. So you can take that 1.5 and basically just add on to it what happens after that, which is now you're another triangle area. This is a 1 by 1 triangle, so the area is 0.5, right? And then it's below the x-axis, so it would be -0.5. So that cumulative total between 1 and 5 is 1. 1.5 minus 0.5 is 1. And finally, just make sure to actually answer the question. Don't expect the graders to infer from all this beautiful work you did. Just make it clear. And also read the question carefully. Sometimes they will say, where, at what x value does it have the maximum or minimum? And in this case, it says, what is the maximum value of h? So looking at these y values, these are the values. The maximum one is 2 plus pi over 2. So I always like to kind of say both things just because I feel like it's a good habit and it kind of covers you both ways. So, and what I mean by that is I will say the max value is 2 plus pi over 2, which occurs at x equals -3. Even though they didn't ask for that, if they did, I would have been covered if they asked where it occurred. And there we go. So there's 5 classic parts to an FRQ, which you definitely want to know if you're taking that exam, which is interpreting a derivative of a graph. And if you practice these, you see, if you look back on the real ones, they are extremely similar year to year. So do yourself a favor and be comfortable with these, and you can really crush it and save time and get to the harder types of problems that they are going to have on there, because they always do have some tricky ones. But this one's usually not too bad. So hopefully this helped you review. If you got any questions, let me know, and keep working hard.